Lab 3, Black Hole Orbit. The purpose of the lab was to analyze the movement of the star revolving around the black hole and determine how gravitational force and Newton's second law is applied to the system by using the BPython. The lab will be focused on the fundamental theory of the momentum principle, or Newton's second law, which states change in momentum equals net force times change in time, which can be rewritten as dp over dt equals net force, where both dp over dt and net force can be separated into perpendicular and parallel components. The dp over dt perpendicular is affected by change in direction, while dp over dt parallel is altered based on the change in speed. The net force acting on the system in the space for this lab is the gravitational force of the black hole, which states F gravitational force equals negative g times the mass of the star times the mass of the mass of the black hole over magnitude r squared, where g is gravitational constant 6.67 times 10 to the negative 11, and r is the distance between the star and the black hole, which can be calculated using the position of the star minus position of the black hole. Before showing you the Python model which gives us the visual representative, I will explain the code briefly. The star's mass was 1.989 times 10 to the 30th, and black hole's position, which does not change, is 4 times 10 to the 10th and negative 2 times 10 to the 10th, y component and x component. Gravitational constant is 6.67 times 10 to the negative 11, and delta t was 86,400 seconds, and t initially was 0. P initial and P final was calculated using the mass times velocity, and delta V over delta V and delta P was calculated by subtracting the initial velocity and momentum from the final. The dp dt was calculated by dividing the delta P over delta T, and F net was set equal to this. And the parallel component and the perpendicular component was also calculated using the same formula. And I'll show you the code now. So this is the visual representative of the star orbiting around the black hole, which is black dot here. So, as you can see, the star moves from A to B to C to D. And there is 3 arrows represented here. The yellow arrow represents the net force, which always points toward the direction of the black hole, because only force acting on the star is gravitational force, which is exerted by the black hole. The blue arrow represents the dp over dt perpendicular, which always points toward the center of the kissing circle, which you draw tangent to this point of the star, right here. And the black arrow represents the dp over dt parallel, which points in direction of or in opposite direction of the star's movement, depending on whether the star is speeding up or slowing down. So as you can see, from A to C, the black arrow is actually pointing toward the star's movement, but in D, the black arrow is pointing opposite direction, because as it approaches the black hole, which is pulling the star, it is speeding up because its force is getting greater, but as it goes away from the black hole, the speed is slowing down and causing the black arrow dp over dt parallel to point in opposite direction of the star's movement. So what does it mean? In your analysis, you should discuss how net force differs from dp over dt. So, the net force differs from dp over dt because even though we calculated net force by setting it equal to dp over dt in this lab, dp over dt is the one that is actually caused by the F net, not the other way around. In other words, the momentum is conserved unless the net force or force is acted upon the system, which then causes the change in motion according to the momentum principle. Therefore, net force and dp over dt can definitely have different value in certain times, because while force is being applied to the system, the value of the dp over dt keep changing in response to the force. Then what is actually causing the difference? According to the Newton's second law, dp over dt can be written as m times a, where m is constant value. With that in mind, the only changing factor in this equation is the acceleration. This acceleration changes depending on the force applied to the system, and because it is change in momentum over the given time, not just the momentum at a certain time, it could be different from actual force, the one causing the change applied to it. So what if, imagine the black hole whose mass you found was removed and a different black hole was placed in the same location. Assume the motion of the observed star remains unchanged and is affected only by the gravitational force of the new black hole. Could you tell the difference? No, you could not, because if the star is the only affected by gravitational force, and the black hole is placed in the same place as previous one, all of the variable used before was constant, or becoming constant, therefore giving the same value of the mass of the black hole. In conclusion, while the star is orbiting, the black hole may have many other factors that shapes its behavior and movement. The main fundamental idea that describes its motion is behind the Newton's second law and momentum principle. The gravitational force, the net force acted upon the system, causes the star to speed up or slow down dp over dt parallel and turn in oval-shaped form dp over dt perpendicular.